Machine learning in a nutshell. So let's get started. Right, so I'm assuming a bit of prerequisite familiarity here, some fundamentals like scalars, what are scalars, vectors, and matrices, spaces, sets, and transformations. I'm also going to show a demo in IPython Notebook, so I'm assuming that you're familiar with Python and some of the associated libraries. Okay, let's get started. So what is data? Starting with the real basics here. Data, by definition, are facts and statistics collected together in a form that's efficient for movement or processing. Data comes in different forms, as can be captured in the wild. We can have text, we can have images, we can have collections of images back-to-back as video. We can represent data in a tabular format, or we can find them in graphs, and of course other types not shown here. If you have a structured collection of data, this gives you what is called a data set associated with a particular phenomena that you'd like to study. Data comes in different shapes and sizes. One way to categorize data is to say that we have numerical data versus categorical data. Intuitively, numerical data is made of numbers, and categorical data is made of words, or can be represented as words. If we want to split them down further, we can consider numerical data as either continuous, such as age and blood pressure and weight, or discrete, which are things like shoe size and number of children or number of faculty in this department. And on the other branch, when we have categorical data, we can either have a natural ordering to them, such as the first person who was hired in the department and then the second person who was hired, or we can have nominal categorical, which is different maybe types of faculty that exist, teaching faculty or systems faculty, et cetera. And I'm going to ask questions throughout, so I hope to engage you with a bit of participation. Let's consider the example of a solar system, and I'd like you to kind of tell me which one of the categories, the characteristic I'm going to mention falls under. So if we have the ordering of planets, which one of the categories would the ordering of planets fall under? Is it a numerical discrete or categorical ordinal, maybe with a show of hands, or a nominal? Is it ordinal? Okay, there we go. If we have the distance from the sun, which category would it fall under? Continuous, right? If we have the number of planets, that is discrete. Very nice. Okay, you understand the basics. Great. Also on this slide, what I'm showing is an example of GIS data, or Geographical Information System data. An important thing to consider about data is that data is always a summarization or an approximation of some underlying real-world phenomena. In this case, we're seeing that the real world is something about the world. This might be a rudimentary map of Pittsburgh itself. But then we can capture various things about the underlying phenomena that each are various different types of approximations of that data. We could look at either the elevation or where customers lie on this map, or as well as land usage. And all of these are different framings or different lenses we use to look at that underlying real-world phenomena. Importantly, I want to emphasize that it summarizes something about the real world, but it doesn't necessarily capture everything about the real world. Of course, we have other forms where data actually summarizes some real-world phenomena. This is an example of some pixelized version of a camera capturing the image of Abe Lincoln. And we see that if we have a very high-resolution camera, we'd be able to see exactly every detail on his face. But we don't necessarily have to have that to capture some information about Abe Lincoln itself. Specifically, if we have a camera, we need to select things such as what is the resolution of that underlying phenomena that we want to capture, meaning how many sensors in my camera do I have to capture that underlying phenomena, and for each of them, for each of those sensors, how many bit channels do I use to capture that data. So essentially, if you consider we have real-world data here, through a process called media digitization, we can go from that underlying phenomena to a matrix of numbers in this case. And then we can use that matrix of numbers for processing. So data can capture too little information, as we saw in the previous slides. It can be a summary of the data, but it can also sometimes capture too much information, which is sometimes called collinearity of different features that exist. For instance, you folks in the States use Fahrenheit to represent degree of temperature. In most other countries, we use Celsius. And if you have a data set that comprises of both of these together, it's redundant information because there's a direct linear mapping between them. So the number of features that ultimately exist in a data set is called the dimensionality of that data set. And the number of samples for which we have those features is called the cardinality of the data set. If either of these grows to be a very large number, so if the limit of either of these goes to infinity, this falls under the branch of big data. We're not talking about big data today. I've just thrown it on here so you know where we're situated with respect to other sciences in the field. OK, so let's look at a few examples. This, let's say, is the Netflix dataset comprising of roughly 500,000 users and roughly 20,000 movies. It's high dimensional for obvious reasons because these numbers are quite large. And they can, this information gathered together can be used for either learning or recommendation. And one question I want to ask the audience here is that which movies do you think, movies being in each of the columns, are most similar among the ones that you see here? Top Gun 1 and Top Gun 2, right? And why is that?
Similar genre.
Similar genre, similar name, similar rankings between individuals, right? Seems like Layli, who didn't like Top Gun 1, was also barfing at Top Gun 2, right? And same with some of the other individuals. What about the individuals? Which ones seem similar? It's a bit harder. Susan and Layli, and why is that?
They have similar ratings for the two top movies.
Right, okay. Who else would you say are similar? Also maybe in the back.
Tom and Akbar.
And why is that?
They both hated Titanic.
They both hated Titanic, good, yes. And at the same time, we know that the Top Guns are somewhat similar and they have, relatively positive responses to those. Right, so the fact that we can the fact that this data is very large and there's missing pieces in it shouldn't dissuade us from trying to infer some form of, inference from this. We already see that Top Gun 1 and Top Gun 2, not just by their names, but perhaps from other information we have from elsewhere, are similar. And we can see that maybe because of the similarity between different individuals, like Susan and Layli, because we know that they had similar responses to Top Gun, then maybe we can predict how Layli would like something like Lion King. And so large data gives us this ability, even though we have missing data, gives us the ability to make inferences about other parts that we are not so sure about. This is another data set. This is Professor Brendan Fry from U of T. He took a webcam and recorded his face, making different expressions. Each of the images are 20 pixels by 40 pixels, so 800 dimensions, and there's a total of 2,000 images. I know they're small, but do you observe any differences between the images here? What do you think changes between each of these frames?
Smiling versus frowning.
Right, so the facial expression changes. Maybe the direction of his face changes. He's looking this way, whereas he's maybe looking in the center. Right, and importantly, it turns out that although these images are 800 dimensional images, 20 pixels by 40 pixels, there isn't that much degree of variation. And if we, through some process, magical process we'll talk about soon, if we're able to look at the data in some lower dimensional space, in this case 2D, we can see that each one of the segments on the image on the right corresponds to some of that underlying degree of variation, which isn't so high dimensional. So in this case, if you go from top to bottom, you see the direction of his face changes. But also here, he has maybe a smiling face, and there he has a surprised or a neutral face, or some funny expression. And what this shows us is that we don't need to necessarily think about data in its very high dimensional, 800 dimensional space, which kind of messes up a lot of things we want to do downstream. But if we can find those few degrees of variations that exist, then maybe that can help with our processing. This is also another example. This is called the Swiss roll data set. And it turns out that we can look at this and imagine that, but the data actually lies on not 3D, but a 2D manifold. So if we can, through, again, some process, maybe preserving the locality of the neighborhoods of each of the points that exist within our data set, we can, yes? What's a manifold? So intuitively, because this is a gentle introduction, a manifold is really just a surface upon which data lies. The surface itself can be embedded in a much higher dimensional space, but the surface can have the lower dimensional dimension. Yes. Right, so if we consider that this is a 2D manifold embedded in some 3D space, which we humans kind of see in 3D, we can unroll the manifold and actually look at it on a two-dimensional surface. And so again, this suggests that maybe we don't have to always take data at face value, and through some pre-processing steps, which is dimensionality reduction, through some pre-processing steps, we can come closer to the actual dimensionality of the data. Okay, so I already mentioned dimensionality reduction, so let's actually define what it is. Formally, it is the process of finding and embedding x tilde, which is a set of a number of elements, x1 through xn, all of them tilde, in some k-dimensional space. And this embedding corresponds to some original data set, same cardinality, in some higher dimensional space, D. Dimensionality reduction, as motivated on the previous slides, primarily is done to overcome what is called the curse of dimensionality. And it's a curse because if we have too many features, too many redundant features, all of the downstream algorithms we want to run, most of the time they run into trouble. So the advantages are obviously removal of redundancies, like the multicollinearity that we saw in Celsius versus Fahrenheit. As a result, we see a reduction in time and storage space requirements. And also sometimes, if we can come to 2D and 3D, we can visualize data sets as humans. Is there anyone here that can visualize in more than 3D? I'd like to talk to you. OK, I guess not. OK, there are various ways that we can split or make a taxonomy out of dimensionality reduction methods. One of the simplest ways is to say that we have two approaches. One is called feature selection, and the other is feature extraction. Feature selection says if I have some d-dimensional data set at the beginning, I'm just going to select a subset of those dimensions and throw away the rest without any consideration for what information exists there. And then d prime is smaller than d, so I'm shrinking the dimensions. It's pretty straightforward. It's simple, but it loses a lot of information. And like I said, we're not really considering the information that's lost. Feature extraction, on the other hand, is a learning-based approach. It could be a learning-based approach where we're trying to find a transformation, it could be linear or nonlinear, of this original data set into some lower dimensional d prime space, whereby this embedding is the result of some function that is either learned or approximated of the original data set. So let's look at what this looks like in some real-world data. Right, so I can circulate this notebook afterwards if people are interested. So we have a famous data set part of the UCI library. It's called IRIS. And IRIS has 150 samples across 4 dimensions. It corresponds to this iris plant. And each of these plants have 4 dimensions. So they have the sepal width and the sepal length and the petal width and the petal length, as we can see here, corresponding to those dimensions in a table. And if we were to visualize this data set, we can't because it's in 4 dimensions. However, through a process which I haven't defined yet, but it's called PCA, we'll see in a couple of slides. Through this process, if we say that I want to project into 2 dimensions, then I get an embedding that looks like this. So there were 3 classes of flowers in the iris data set, and it turns out if I project down using this PCA approach, then I can see various patterns exist across these different classes. And the transformation specifically that was used is something like this. So it says that take the first dimension and multiply it by 0.361, and then take the second dimension, multiply it by negative 0.085, etc. So we're actually taking all of the information from all of the dimensions that we have. We're finding this transformation. The transformation was found through this process called PCA, which we'll introduce soon. And then together, that transformation maps the data into what we see here. Now, a question you may ask is this the only transformation we can find? And the answer is no. There are different types. Turns out that there are some very nice properties of PCA, optimality, minimal loss of information, and all this. But of course, you can find different methods. Are there any questions? OK. OK, so 2 flavors, feature selection and feature extraction. When we're trying to find these transformations, again, the transformation is going from some, I guess this is on autoplay now. Let me pause that for a second. Right, so transformations are trying to go from some high dimensional space to some low dimensional space while preserving as much as the relevant information as possible. In a domain where we have associated Y labels for data X, which is not the case we're considering here, but in that domain, we're reducing the number of features while at the same time preserving the relationship that exists between the X covariates and the Y targets. In the case that we're studying today, we're trying to find a lower dimensional representation that preserves as much as what is called the original structure. And we'll see that the structure corresponds to the variance that exists in that data set. To add some names in case you want to jot them down and look them up afterwards, in the case of supervised dimensionality reduction, we have LDA for linear methods, and we have neural networks or autoencoders as a nonlinear approach. And when we do not have labels for unsupervised dimensionality reduction, we have PCA or principal component analysis, which is the focus of today's lecture. And we have, again, isomaps or other forms of neural networks to do nonlinear transformations. OK, so we're talking about PCA. And like I said, it's a linear method for linear unsupervised technique to reduce the dimensionality of the data. What we're ultimately trying to do is we're trying to go from this data set here, which is in how many dimensions? 1, 2, 3, 2 dimensions, good. To this data here, or the red points that exist on that line, which is how many dimensions? 1 dimension, perfect. Right, so we're trying to go from that to preserve as much as the variance that exists, or as much of the information or structure that exists. There are some equivalencies just to give some intuition here. So when we say we want to preserve as much as the structure in the original data set, what this corresponds to is retaining directions of maximum variation. So we want to find the projection that retains that most of the variation in the data, which curiously corresponds to reducing the residual error that exists between the embedding and the original data set. OK. So let me just skip back. Again, this is what we're trying to achieve. Over the next few slides, we're going to look at them step by step to go from the left figure to the one on the right. The first thing we do is to subtract the mean of the data. We can compute the mean just like how you would compute the mean of any sample of some population. And then we subtract that from the data set. This is required for the downstream covariance computations that we need to do. This is what it looks like. It's called centering. We take away the mean. As a next step, we compute the covariance matrix that exists between the different dimensions. Covariance, if you want to intuitively understand it, it tells us how the distribution of the data co-varies across its different dimensions. To see a few of the examples, this data has, of course, the labels on top, but it has positive covariance because as x increases, y increases at the same time. On the flip side, if as x increases, y decreases, then this is a negative covariance. And if there's almost no change across the dimensions that covary with one another, then this is zero covariance. We're computing the covariance, again, because we want to find those dimensions or those directions in which the data varies the most, so we can retain those, corresponding to minimum information loss. The next step, which is a bit of a daunting step, is what is called eigendecomposition or eigenvalue decomposition. If you only want to consider what this means intuitively, this means that once I have the covariance matrix of our data, once I know kind of the directions in which or how much the data directions in the original basis space vary together, then I want to find a new basis in which those new bases actually aligns with the directions of variation. So eigendecomposition gives me two things. It gives me eigenvectors, which are vectors that I consider as new bases that point in the direction of variation in the data. And corresponding to each of those vectors, I get what is called an eigenvalue, which intuitively is how much along those directions that are pointed by the eigenvectors does my data vary. I'm going to pause for questions in case there are any here. Yes?
There was a term on the previous slide, scatter matrix.
Right, so a scatter matrix is basically, it's represented as the mean subtracted x times x transpose, and it corresponds to how pairs of data points are related to one another. And then we use that to compute the covariance matrix.
What's the relationship between the scatter matrix and the covariance?
Well, it's basically the covariance matrix is defined as the scatter matrix, normalized by the number of points. Yeah.
Sigma is the covariance.
Yes. Yes. Okay. So again, just to reiterate this point, we have an original basis that need not align with the bases that align with the directions of variation. Through the process of eigendecomposition of the covariance matrix, we get eigenvectors pointing in the directions of variation and eigenvalues telling us how much variation lies across each of those dimensions. Okay, so depicting this in a diagram. So if this was initially x and y as original bases, through this eigendecomposition, it seems as if I'm changing my bases, and now my x corresponds to the direction of variation, and my y corresponds to another direction of variation. Interestingly, and this is a very powerful property of eigendecomposition, the result of eigendecomposition is that the order in which I get my eigenvectors and eigenvalues corresponds, basically the matrix that I get is sorted in the order of decreasing eigenvalues. So in the sense, if I had another dimension here, that dimension would have even smaller variance. So the first dimension has the most variance, the second dimension has slightly less, the third dimension, etc. to the end. Okay. Now that I have a new basis that points in the direction of variation, I need to do what is called model selection, which is basically saying, well, I started with d dimensions. I need to pick k of them because, of course, I'm reducing the dimensionality. And how many k do I select? That's the process of model selection. Once I select k dimensions, I can start from the eigenvector corresponding to the largest eigenvalue and come all the way down until I have k eigenvectors, and that becomes the transformation matrix that I use to perform my PCA operation. So UK is a matrix in RD by k, meaning that you start in d dimensions and you want to go to k dimensions. It's comprised of k eigenvectors. Yes?
When you say peak, you mean the human peaks?
Yes.
So it's not, k is not computed by some algorithm?
No.
Okay.
No. The fact that eigenvectors are sorted by the maximum to minimum eigenvalue itself gives us some guarantees that we're always going to be the best, we're always going to select the best eigenvectors depending on that k that we choose. But that k is selected by a human. Yeah. Okay, so we started again with 2 dimensions. We subtracted the mean. We found the new bases. We selected, in this case, k to be 1 because d was 2 and we wanted something smaller. And so now through that just single eigenvector where there was only one choice, we can project down onto the U1 dimension. If we now reverse the process and project and do the inverse of this basis rotation and add the mean back, we go back to our initial data. And so this is the figure that we saw on the right-hand side of a few previous slides. Okay. Now, one question you may ask is, well, how much data is retained and how much error exists in this projection? And it turns out that there's a nice relationship between the reconstruction error and the lambda i's, where the lambda i's are the eigenvalues that we got from the eigendecomposition. And so we said that we're going to retain everything up to k dimensions. And then starting from the k plus 1th dimension to the dth dimension, whatever eigenvalue we have, sum them up. And together, if you sum up those eigenvalues, this gives the error that exists. It is minimal because of the property that exists in the eigendecomposition such that the lambda i's are ordered from largest to smallest. Questions? Everything is clear. OK, yes.
So if you want to reduce by k, is it the same as keep reducing by 1, 1, 1, 1, 1? That will give q raised to k? Or if you reduce by k all at once, you get something different?
What do you think?
No. That's why I'm asking the question. I'm undecided.
OK. So you're saying if we reduce iteratively by 1 dimension, always reducing the dimension with the smallest lambda I, then would that be equal to reducing it all at once?
Yeah.
Well, in terms of error, it would be equivalent because you're going to start with lambda minus 1, meaning the smallest lambda, and then you're subtracting the rest, and then you're adding up the lambda i's sequentially, or you're just doing it all at once. So these two would be equivalent, yes.
Okay. So really, I mean, you could just talk about dimensionality reduction by 1, and then just say iterate the process.
You could,
Yeah.
but why would you think that's a bad idea?
Well, because you have an additional variable k floating around everywhere,
Sure.
and making it seem more complex than it might be.
Yes.
You only have to do it by 1.
So are you arguing in favor of doing it sequentially rather than in one step?
Yeah, I mean, just,
Because you don't have to take care of k.
yeah.
But wouldn't you still have to decide how many iterations you do? So in a sense, you still do have k. No?
Yeah.
Okay.
True.
I would argue that maybe the iterative process is not so desirable because every single time that we want to perform dimensionality reduction, we have to do this eigendecomposition, which is a bit annoying, let alone it's quite computationally intensive, but let's say it's annoying. And so if they're equivalent, then we might as well just decide in k in advance and go with that.
So you're saying computationally it's better if we do it in big one big step?
If we don't do any clever way of caching, you know, or then yes, it's.
Okay.
But I think there's another point related to what you're asking, which is how many k's do I choose? I know that doing it in one step versus iteratively comes out to be the same, but what should the optimal k value be? And that is a valid question because we need to consider what is a downstream application in which we want to perform this dimensionality reduction. So I alluded to this earlier, but just to emphasize, dimensionality reduction is a pre-processing step, meaning that we take our data, we clean it a bit, and we'll see some applications in a few slides. We clean it a bit, and then we use it for some discriminative analysis or some application, some visualization. But deciding which k in advance and agnostic to the downstream task might not be a good idea. So we might want to test with different k's as well. Yes?
Are the eigenvectors always orthogonal, like in this example?
By definition, they come out to be orthogonal, yes. Or by construction, let's say. Okay. So the goal is to prove that this error is equal to this. And this is not a goal we'd like to pursue in class. So I encourage you to do this at home. I've left the solutions on the slide. You're going to find this resource very useful, the Matrix Cookbook. It really does help at every one of these steps. It's freely available online. And each of these steps you can follow through to then measure the error as the sum of the remaining eigenvalues that we drop. OK, let's look at an example of how many dimensions k to keep. Each of these figures independently, they correspond to two different settings and is called an eigenvalue spectrum. So we said that the eigendecomposition gives us the eigenvectors and the eigenvalues, and they're sorted by largest to smallest. And if we plot them out, we expect a decreasing function, as we see here. Now, a question that I want to ask is, at the same time, we saw that the error corresponds to how many of the eigenvalues we drop. So let's say our original data was 100 dimensions. Let's say I'm going to keep 60 of them, meaning I drop 40. Then if we sum up the values of the eigenvalues that remain, this corresponds to the error. Same here if I sum up the values of the eigenvalues that I've dropped. Now, the question is, which one of these is better in the sense of which one of these figures corresponds to a smaller error in projection? The first one. Show of hands, the first one. Second one.
Is the error normalized? Are errors normalized? Because the scale is very different.
Right. So the scales are different. That was a trick question. The point is, we shouldn't even be comparing eigenspectrums of two different applications. And anytime we do the eigendecomposition of just one setting, we're always going to get the same figure. What this shows us really is that, yes, if I sum up the values of the 40 dimensions I've dropped, that gives me the error in that particular case, which is going to be the unique error every time I run PCA. But these two are two separate settings altogether, as rightly noted, that the scales are completely different. So it might actually turn out that this figure is better in absolute error terms. But that's just a question we don't even want to ask necessarily. So yes, I put this just to trick you, but then also to give you the intuition of how we would compute the error that that we endure when projecting down to some dimensions. So let's look at some applications. This is image data corresponding to the MNIST data set, which I think all of you are now familiar with. It's just a data set for handwritten recognition. Each of the images are 28 by 28 pixels, or 784 dimensions. We want to go from 784 dimensions to some lower dimensional space. Intuitively, when we look at numbers, we would think that they don't lie in 784 dimensions. Digits, we only really have 10 of them. We may have 5 or 6 different writing styles, so 5 or 6 times 10 is really 60 dimensions at most, but not 784. And it turns out that if through the process of PCA, I know the labels are small, but I'll read them out to you. So in the first column, we're retaining 784 components. Here we're retaining 150, 80, 40, and 11. It turns out that we can drop a lot of the dimensions and still somehow understand that this is a 2. Well, it's kind of weird. Or this one's a 7 and that one's a 9. So this also agrees with our intuition that we don't need nearly 800 dimensions to retain the value of the data, but maybe with just 80 or 40 or sometimes even 10, we can recognize digits. Again, we can look at the application of PCA in the scope of compression. This is the image of a butterfly. We can apply PCA to patches on this image. And if I only retain 16, so each of these you can consider as an eigenvector. If I only retain 16 of my eigenvectors, I can still recognize that butterfly. I can still recognize it with 6. It's getting blurry and not so clear. But maybe only with 3 still, I can recognize that this animal is not an elephant, but it's a butterfly. And so instead of retaining all the pixels that correspond to the original data, if I am able to find this clever bases upon which I can use to project my data, then that saves a lot of space and time. Another application is denoising. So this image is again of that butterfly, but I don't know if it's clear in the back, but it has a bunch of little corrupted pixels here and there, which is called salt and pepper noise. It's a cute name. And it turns out that if the amount of noise that exists in my data is not so high compared to the signal that exists for the flaps of a butterfly, then through, again, the process of projecting down onto some k number of eigenvectors and then projecting back up, I can, with somewhat good quality, remove that noise and retain the data that exists. OK. Now, to your question about whether we do it iteratively or all at once, there is, of course, a bottleneck that exists in compute, and that is the cost of computing eigendecomposition. Unfortunately, it's quite costly. It turns out that if D is our original dimensionality, then at least naive approaches to doing eigendecomposition scale cubically with those number of dimensions. Even very clever approaches scale to the power of 2.7 something, so it's quite expensive. Anything that's quadratic or higher is something you'd want to avoid for large data sets. And so the question is, can we do better? And so in the remainder of the slides, I want to just briefly touch on a method that I think is very cool. I hope you also appreciate.
Before you go into something,
Yeah.
could you go back to the picture?
Yes.
So one more. OK, so I didn't quite understand how you go from the right back to the picture on the left. So I can see the dimensionality reduction. You get those 3 things on the left.
Yes.
But how do you reconstruct that fuzzy picture?
Right. So that's a very astute observation. I did skip over a detail there. So what this is actually, how we actually computed each of these bases is that we took patches of size, these are 12 by 12. We took little patches of size 12 by 12 from this image and also from other images that existed within this data set from which we took this data. Using those patches of each of them 12 by 12, 144 dimensions, we computed the bases. I didn't show the other images that existed in this data set. When we had those optimal bases, then we just took them from the order of largest eigenvalue to smallest eigenvalue. And then we projected down and up each of those patches and then stitched them together again. And that gave us the image. Is that more clear?
That's better, yeah.
Yeah, it's a bit of a divergence. I wanted to illustrate kind of the application, but in reality, that's what's happening. We're doing PCA on patches of the data. And let me now ask you this. Why do you think that's a good idea rather than applying PCA to the original image?
Well, maybe the D cube thing has something to do with it.
Right, so the original dimensionality is very large, but now we're getting roughly 100 dimensions that we're going to be taking the cubic power. Yes. Okay. So cost of compute is high. Is there something better we can do? Turns out there's a very elegant method called random projections. So I want to remind you that this was the original data that we had, the dimensions and samples. We found some matrix U, which was the collection of all the eigenvectors corresponding to the largest eigenvalues. We took the product of those two because it's a linear transformation, and then we got our embeddings Y. Now, it turns out that computing the U's was very expensive. But it turns out that there are clever ways of constructing this matrix, I'm not calling it U anymore, some R, corresponding to random projections, such that if each of the coefficients within R are sampled from a Gaussian distribution, so completely independently at random, then that also gives us a somewhat good embedding. It's counterintuitive. I'm not going to go into the details of the proofs and everything. But what it boils down to is to the fact that we said when we want to project from a high dimensional space to a low dimensional space in an unsupervised fashion, we want to preserve as much of the information as possible. In PCA, we said that information corresponds to maximum directions of variation, but there's alternative ways of considering what information is. Information can be seen as pairwise distances between points. So if I have 2 points in a high dimensional space and they have roughly some distance between them, and also other points, if I now project to a low dimensional space, I want relatively the distances to remain the same. And so this complicated slide here, what it really says is that it's a Johnson-Linden-Strauss theorem. And it says that if I have some integer n corresponding to some number of samples in some d-dimensional space, then my k, or my projected dimension, if it's larger than some value, which I'll briefly describe now, then with high probability I get that the distance between the embeddings of any 2 points is bounded above and below up to some tolerance by the distance that exists in the original space. Again, the proof is a bit involved, so we're not going through it, but intuitively what you should take away is that preserving structure can either be preserving maximum directions of variation or preserving relativeness of the pairwise distances. Now, the interesting fact about this theorem is that this new dimensionality k has no dependence on the original dimension d. You don't see any d in that lower bound. You only see n. N is the number of points. So your d could be 1,000,000 dimensions, it doesn't matter. It could be 100 dimensions, it doesn't matter. Your k is bounded below by the number of points that exist, and that should be somewhat intuitive because we're trying to say pairwise distances between the number of points that is there is what kind of determines the lower dimensionality for our guarantees. So yes, k can be very small. It also has a log relationship with the number of points, yes?
So in equation 2, you talk about probability greater than 1 minus delta.
Yeah.
Where is the randomness coming from?
The randomness is coming from the fact that f itself, which isn't shown on this slide, f itself is r transpose x. And r has coefficients that are randomly sampled from a Gaussian.
Okay. And so this doesn't depend, so the randomness comes from the sampling of x, essentially. Is that?
The randomness comes from the random directions that correspond to the bases spanned by the coefficients of the random matrix R. So x is fixed.
Oh, okay, so I thought 2 was independent. So 2 holds, right, independently of how I'm picking f, right? So I can pick f to be a random linear transformation.
Yes.
But there are other ways to pick f, right? And do they have to necessarily be random? Is that?
This theorem is saying that there exists a map. And then how you construct that map is through the proofs that are not shown on the slide. But you could construct f in different ways, and you'd probably get different relations on the lower bound for k.
Right, and so I guess I was just a little bit confused about where the randomness comes from if f isn't necessarily a random transformation.
Right, f is a random transformation, right, yes.
The random transformation has to depend on delta.
The random transformation,
The random transformation has to have some structure to it, not
Well, equation 2 and 3 are just the same thing. It's just a more compact representation. The probability of this being larger than delta, so this not being satisfied, is smaller. Sorry, this being larger than epsilon, so 2 not being satisfied is larger than delta. It's the same thing of the expression above.
So what does delta depend on? Or is delta just some arbitrary constant? We have some.
Right, so delta and epsilon go hand in hand. So if we select our delta, the probability that we want, then epsilon comes out of that. The relation is not shown on the slide here, but it's just like any other random proof. We say that with probability something, arbitrary threshold, then we get some tolerance, or the opposite direction. We select the tolerance, then with some probability our equation holds.
How are epsilon and delta related?
That's what's not shown on the slide here.
Okay.
Yeah.
I feel like that's important because otherwise we're just saying with probability, with some probability.
Yes. No, absolutely. They are not independent in that sense. Yeah. Okay. Right, so random projections, this theorem says that such a transformation exists, and the proofs by Indike and the rest of the folks here show us how to construct various random projections for that. To summarize and to put these two methods kind of on the same slide, so you get a visual intuition of them, PCA finds us the direction, the optimal direction for linear transformation, but it's expensive. On the other hand, random projections gives us a random direction upon which we can project, and it turns out it does quite well. Yes?
So the components sampled by random projection will not necessarily be orthogonal.
No. No. But in the interesting thing is, in high dimensional spaces, random vectors are approximately orthogonal. And so they might not correspond to the best directions of variations, but because they slowly pick up this property of almost being orthogonal, then the more you have, the more information you retain, even if they're not ultimately the best directions. And this is the end of the slides, but just for those of you who are curious, this is actually the core of a method called locality-sensitive hashing, or LSH. And it's widely used in search because you don't want to be comparing very high-dimensional vectors together to find the nearest element in some database. Using random projections, you go from your high dimensions to low dimensions, and you do approximate search, and it does very, very well. So, yeah. Happy to take questions. Otherwise, see you in the next lecture. Okay.
So what's the target audience for this lecture? Which course, which level?
So this was an undergraduate course. I'm trying to go back just to get the course number. This is Professor Gianni's course at CMUQ, ML in a nutshell, maybe lecture 4 or 5 after basic introductions to what data is and all that. I did repeat some of the stuff, but the course number is 15-288. Undergraduate, mid-level undergraduate course.
So presumably they have taken linear algebra before they take this course.
For these slides, they would need linear algebra, yes, and intro to Python to see at least the Python notebook and all that. Yeah.
When you do, is your thought that when you pop into the Jupyter notebook, students can follow along so that material is available to them before and they can?
That would be ideal, yes, to pass those around in advance. I mean, feedback is much appreciated too. I'd be happy to improve on these and get much more experience in this regard.
So how sort of deep does the course go? It's called ML in a nutshell. Is the idea that it's kind of intuitions about a broad range of techniques and topics, or do you, like in a future lecture, say, would you dive back into Johnson, Lynn, Strauss and actually show some of the tendencies?
So there's 2 parts to your question. The second part is easier to answer because I didn't design the course. I think not. We would not go back into the Johnson, Lynn, and Strauss. This is something that involves, you need to have taken a lot more advanced courses, I think, to understand. This was what I worked on during my master's on nonlinear random projections, so I spent quite a bit of time trying to understand what was happening behind the proofs. It's quite elegant, but understanding it requires a lot more knowledge. I would think that a good way to end a lecture is to end it, okay, the way that I did, in the sense that you give some real-world application. Look, this is a very complicated thing, but it turns out what you're learning is the basics of these complicated things that we use every day, but not necessarily going back to, trying to understand Johnson, Lind, and Strauss. If the course if the course syllabus has a lot of dimensionality reduction involved in it, then perhaps a couple more methods besides PCA would be useful. Things like isomap, because they also talk about locality and all this. But it really depends on the audience, because again, linear algebra in Python is probably the most basic things you need for this, but it can quickly diverge from there. Yeah.
So like the students would never necessarily need to understand the formal statement of Johnson.
No. I think if you were to ask what a good exam question would be, it would mostly try to touch on the intuitive parts of kind of the questions that you and I talked about. Why would we use patches, and why not do on big dimensions? Or if I have some spiral data set, what would be the directions of variation? What would you think the principal components would be? Stuff like this. Now, if they're a math-heavy audience, then you actually have them derive some basic stuff as well.
And what would be a good homework assignment? This is a good exam question, but what about homework assignment?
Maybe implementing PCA. So we, of course, have PCA that exists in things like scikit-learn already, so they could use that as a benchmark for how good of a result they could get. But actually implementing it out and using maybe they probably would be able to use like SVD to get the principal components and all that. But then actually applying them, doing the matrix transformations, I think that would be a good entry-level exercise. Again, I'm thinking maybe like undergrad, year 2, year 3.
That seems pretty ambitious to me.
But this is CMU, no?
Well, I haven't taught this kind of stuff here, so I don't know.
Okay.
I could imagine that, you apply it to a given new problem, maybe not character recognition, maybe some other, I don't know, Arabic characters or something like that.
Yeah.
But I guess I'm not sure how easy the packages that one would use are to actually use for a new problem.
Okay, I see.
I guess kind of related to that, you said familiar with Python is one of the objectives sort of in a course like this, or if you taught, would one of your objectives be to sort of get students very familiar with very commonly used packages like NumPy and what's in scikit-learn, things like that?
I would, that depends on whether they've been exposed to it before or not. So I guess we can't really look at this course in isolation of what the curriculum of other courses has been. But yes, it could take very much an applied sense to it, where they're already familiar with NumPy and these packages, and they apply various approaches to some data set. And otherwise, then yes, it would have to be watered down. Yes?
I have a general question. So a lot of these algorithms are implemented traditionally in Python,
Yes.
but they also are very computation intensive.
Yes.
So why do them in Python as opposed to something else that gives you much faster executable?
That's a good question. Are you asking in the context of like a course design, or?
Machine learning in general.
Okay. I guess if you have someone whose work is this, then naturally they'd start off with like a prototype in some language that's accessible, and then go, use MEX or C++ or something to implement them. And there are implementations like that out there. I would think that the field of machine learning specifically is so broad these days that it's always trying to find the balance between breadth and depth. And what you're suggesting goes a lot in the depth of not only implementing the algorithm and figuring out what's optimal and what's not, but implementing it in an optimal manner on some specific hardware, compiler, or whatever. That would be you'd have to be very into PCA to want to do that. As a student, I would probably find more value knowing kind of the tools that exist, even if those tools aren't optimally implemented. And then figuring out how to best apply those tools. Or in which scenario would I use an autoencoder versus PCA or stuff like this. Yeah. but that's my bias. I don't know. What do you folks think?
I guess some of these packages, like a thin layer of Python over some
There is.
code anyway.
There is, yes. I understood the question to be like, should the students be learning not only to implement them in Python, but also in some of the lower languages? And that might be a bit too much. Yes?
Given that this course is fairly early in the sequence, you'll probably still get a whole lot of students with a wide variety of experience with things like, maybe they've taken linear algebra, but some of them are going to be super comfortable with it, some of them not so comfortable with it.
Yeah.
How might you structure the course so that you keep the top students engaged while supporting sort of the students who are less comfortable with the fundamentals they need to know in order to grasp these sorts of algorithms?
Yeah. That's a good question. I think, yeah, thank you. Again, this is very much open to feedback, but the way that I structured the slides, I think it was like 25 or something, where I had the proofs there as a homework exercise. Potentially this could be like extra marks. I don't know if someone wants to go and the proof is there, but like write something up about what it means and what the steps are. I think that way would engage the very top students, but also I tried within the slides to have intuitive footnotes as to what this actually means, because at least that's the way that I like to learn, which is, there's the math, and some people love the math, but some people find it dry. So getting that intuition is what I would want everyone to understand. Because even for myself, like understanding some of the concepts in linear algebra really takes time. But building that intuition is something that you kind of need for the foundations of everything else on top of it, even if you can't do a proof by heart. So those extra, to answer your question, the extra parts within the notes would be something to keep the top students engaged.
Thank you very much.
Of course, thanks for coming.